Hello and welcome back. Now we're going to start with another large module. In this large module, we're going to go through the complete synthesizable subset of Verilog, using examples to illustrate each of the types of statements we can make with Verilog. It's basically broken up as the outline here. We'll start with procedural examples before moving to operators and continuous assignment, before going to structural Verilog and also looking at some common problems and solutions, and finishing off with some more sophisticated examples. I want to remind you before proceeding that a core tenet, a core mantra in this course is always design before coding. This is very important to remember, and we'll see examples of what happens if you don't do this when we look at some common problems and solutions. So this is broken into three main units, and each of them has 2 or 3 submodules. In this, the first submodule, the first unit, in this unit we're going to look at procedural code, literals, flip-flops, and behavioral logic, and we're going to start off with literals in this particular submodule. Within this unit, what I want to do is look at all the aspects related to procedural coding in Verilog besides operators, which we'll get back to later. In particular, I'm going to go through numbers, how they're specified, what they mean, how procedural code is structured, the difference between blocking and non-blocking assignment, and lots of examples of how to specify logic using procedural code. My motivation here is to go through a fairly complete subset of the Verilog language that is useful in synthesis, and in particular justify why I use that funny assignment when assigning to flip-flops, and why I strongly encourage you to use that when you're building flip-flops. And finally, show you how procedural code can be very useful to capture the behavior of a very complex logic block without having to deal with its internal structure at all. These are the references for this particular section, are spelled out in quite a bit of detail. I remind you of the reference at the bottom here. The Sutherland Reference Guide is a very nice but concise guide as to how to use Verilog. Before I do this, I want to go through a short example to illustrate some of what we've learned today. So here's a simple example consisting of 3 blocks of code, and in this I've used each different type of code structure that is synthesizable. Building flip-flops, building combinational logic with an always statement, and using continuous assignment to also build combinational logic. What I'd suggest you do is pause this recording for a moment to think through what this logic structure looks like and what the timing diagram might be for this one particular clock edge. Well, this is that logic structure. Always at pos edge clock builds a flip-flop A with B and C going to an OR gate at its input. The second procedural block builds an inverter who's connected to the output A of the flip-flop. The third procedural block builds an XOR gate connected to the output of the inverter and the input C. And remember, these 3 different code blocks here are all independent of each other. Because the Verilog simulator captures the intrinsic parallelism of hardware, it does so such that you can write these in any order you want. I can put the assign statement at the top of this example, and this will be perfectly correct. Then let's look at a simulation of this around the 1 clock edge. B or C produces 1 at the output of the flip-flop after the rising edge of the clock. That gets inverted, and then the XOR gate creates 1 as well. Here I'm showing them with a slight delay. In the actual Verilog simulator, you won't see any delay in the combinational logic because it does not model delay in combinational logic pre-synthesis. It's only after synthesis, when you know what the gates actually are, that you can start predicting combinational logic delays. So let's turn to how you specify numbers in Verilog. We've seen examples of this already, but this is the complete description of how this is done. There are 4 different logic values in Verilog. 0, meaning 0, or false, 1 meaning 1 or true, Z for high impedance, which also means the node is floating, and I'll explain that in the next in a later unit, and X for unknown, uninitiated, or don't care. It so happens in Verilog that the start of simulation, all variables are initialized as X. This is actually quite useful because you don't accidentally think that you've already written to a variable. In contrast, VHDL initializes everything as 0. Well, we've already seen the structure here for specifying numbers in Verilog, where we have this trio here that specifies the size of the number in terms of the number of bits, the base, binary, hexadecimal, or decimal, the most common ones, there's also octal, and the value in that base. Below here I have some examples. Before I do that, I want to highlight a few issues that help you understand how these numbers are understood within the Verilog simulator. The default is 32-bit decimal. So if you just write a number, that's what you're specifying, a 32-bit wide decimal number. Unspecified high order bits are 0 filled if the leftmost bit is 0 or 1. If it's X or Z, that is what is filled. I'll talk about that in a moment. High order bits are truncated if the size is smaller than what it's assigned to. So let's look at the examples we have here. Let's look at the first three on the left. Well, when I just write 10, or 10 is shown here, I'm actually specifying a 32-bit decimal number. So 10 in binary is 1010, and it'll be 0 extended out to 32 bits wide. 8HF0 is quite straightforward. F is 1111, 0 is of course 0. 5D11, 5 bits wide, decimal 11. 11 in binary is 1011. The fifth most left bit is 0 because the number is 0 extended to give the amount. Now let's look at the examples on the right. 3-D5, it's quite straightforward. 5 is 101 when it's 3 bits wide. 8HF, 4 zeros to pad the left-hand side of F. 2-B10 is exactly how it specifies. I didn't illustrate the example on the point on the bottom right here. For example, if this example here was 2-D5, what would be the number that's specified? It'd be just 01. The third bit that's above the size would be truncated. Now let's look at X and Z. X means don't care or unknown or uninitialized. Z means high impedance. That is, the signal is not being driven from at least this source to a specific logic value. Let's look at what that means. You might recall how high impedances are produced at the circuit level. On the left, I have an example of a high impedance inverting buffer. I have NFETs at the bottom here. The NFET is on when the gate is high. And PFETs at the top here, you might recall the PFET is on when the gate is low. So in this example here, if S is 0, then this gate is off, and this gate is off. That means out is disconnected from any input driving it, at least within the circuit presented here. That means it's floating, or in the high impedance state, high impedance being, of course, that when these gates are open, they're presenting a high impedance from out to any signal that's possibly driving it. Of course, when S takes on the value of 1, S bar takes on the value of 0, and now both these gates are on, then this circuit acts like a normal inverter, just inverting D onto the output out. The bottom here are the rules about extension. If you underspecify the values here, if X or Z are the leftmost bit in what's specified, then they're self-extending. So for example, 8-BX0 was BX0, but we need the other 6 bits. Since the highest specified bit is X, it's X extended. And we'll come at the 3-BZ, we're only specifying 1 bit Z, but that will be Z extended. And I'm just illustrating here one way to write numbers so they're more readable, and that is by putting underscores typically between the nibbles or 4-bit groupings, and this is used very commonly to make the numbers more readable. In Verilog 2001, there's also the concept of assigned values. And that is specifying by this S in the number. That denotes that the value is assigned, which implies that other values are unsigned. This doesn't change the actual value. It doesn't do 2's complement or anything like that. In fact, that's done normally if you put in minus. But what it does change is how some of the operators deal with that value. For example, do they assign extended or not? We'll come back to this when we look at operators. Apart from that, the everything else in specify is the same. So here's an example. Here's some examples. 4-HF is just 1111. 4-SHF is also 1111, but with certain operators will be interpreted as -1. 6-SHF is 001111. In this case, it actually doesn't make any difference because this is a positive number in any case. So if you specifically want to have sign extension and things like that happen, and this mainly is in the arithmetic shift structures, then you need to use this S when specifying numbers. Some other things here about lexical conventions. As well as underscores being ignored, spaces and new lines are also ignored, so you can use spaces to make numbers more readable. Verilog is case sensitive, so be careful when typing variable names to make sure to preserve the case. Variables can have to start with a character and can only contain characters, numbers, underscore and dollar. And of course, reserved words such as always cannot be used to specify variables. Next, look at the 2 basic data structures, or really one basic data structure in Verilog, and that is a vector of bits. We're modeling hardware. You either have a wire or a bundle of wires. Well, that's all we have in Verilog, is a bit or a bundle of bits, or more properly referred to as a vector because it's specified in a vector format. So vectors are declared by specifying a range of bit numbers and the variable name. You can specify high to low or low to high. I suggest in general you stick to the high to low format, the big endian. No specific advantage to it, but it's more consistently what is used by designers. And if you mix both of them together, it can be very confusing. Is bit 0 the most significant bit or the least significant bit? If you just stick to big endianness, you know which is which. So here's some examples. Wire 7:0 bytes declaring an 8-bit data called byte. Reg 15:0 info is declaring a 16-bit register called info. Of course, reg means that it's assigned in a procedural block, not necessarily the output of flip-flops. And wire means it's assigned using continuous assignment, or it's the output of a module. Here's a little endian example. Reg 0:11 data, that's declaring a 12-bit register named data, with the most significant bit being bit 0. In contrast, in info, what is the most significant bit? It is bit 15. So big endingness, as specified down the bottom here, is the most typical way in which to specify vectors by an informal convention. Now that you have a vector, you can specify individual bits or bit ranges within a vector. And this can be quite useful when you don't need the full vector. For example, you can specify one bit, such as bit 5. You can specify a range of bits. Here we're specifying a range of bits from info. And here I'm specifying 1 byte, the least significant byte, of a wider variable data. There are also arrays available within Verilog. These are basically arrays of vectors. You can have 1D and 2D arrays. Later we'll have an example of a register file where we're building an array of registers. What we're going to do is it'll be declared like this: reg15:0 to build a 16-bit vector, register file 0:31 to specify a 32-bit array of those 16-bit vectors. And we'll see this example later on within this module. I won't present you an example of 2D arrays since I've actually yet to count a case where it's actually useful. But Verilog 2001 does permit it. Note, arrays cannot be passed through the input-output ports. You can only pass vectors through input-output ports. If you need to pass an array, you need to make some assignments to turn it into a vector that can be passed through it. And we'll see an example of that in the complex design notes. So in synthesizable designs, register files and unsynthesized memories are often specified as 1D arrays. We'll see the register file example later. And 2D arrays, at least in my experience, have a little value. There are other data types within the Verilog language. There are integers, which do have one use in synthesis, that is as a loop counter, and we'll see that later. And there's also real numbers and time. These can only be used within the test fixture. They are not useful within the synthesizable Verilog. So that brings us to the end of this particular submodule. Mind you, the main points herein. The lexical rules allow us to specify numbers using the size, base, value format. Size is number of bits, value is in terms of the base. Remember, the default is 32-bit decimal. I do encourage you to specify numbers precisely. For reasons we'll see later, if you have 32 bits within there, the operators are expanded out to 32 bits. And I talked about the rules for how the unspecified bits end up being specified, quite simply by padding it with zeros, or X and Z if the leftmost bit is that. And really, all signals in synthesizable Verilog are bits or vectors of bits, and occasionally we'll see an array. And now what I suggest you do is do the quiz associated with this submodule before proceeding to the next submodule. Thank you very much.